All right, so let's walk through this example of how we're going to find a fishing level. So our population of 1,000 fish is growing at a rate of 50% annually, and the lake is restocked with 500 fish each year. We want to know what percentage of the population we should be fishing each year to reach the desired equilibrium level of 4,000 fish. Okay, so we are trying to find the fishing level, and then we're also going to try to write a difference equation. All right, so the first thing that we should do, recall that our n is equal to the number of years, and our x sub n is the fish population. All right, we have x sub 0 equals 1,000, and then x sub n plus 1, that's the fish population next year, is going to be equal to, so we start with the growth rate. Since the growth rate is 50% of the population, we write that as 1.5 x sub n. And then we know that there's going to be some fishing involved. So let's go over here. Let f be the fishing level each year. All right, and that, we'll just label that as f. That's going to be some percentage of the population, so we're going to write it as f times xn. And then we also have a restocking level of 500 fish, so we write plus 500 here. All right, now we're trying to get to this equilibrium level of 4,000 fish. So what we're going to do, instead of kind of trying to solve for the equilibrium level, we are going to force the equilibrium level to be 4,000. And the way that we do that is to replace x sub n plus 1, x sub n, all of those in our equation with the value of 4,000. Okay, so kind of like we replaced xn plus 1 and xn with L. This time we know what the equilibrium level is, so we're going to replace those all with 4,000. Plus 500. All right, so now this gives us an equation with one unknown, specifically the unknown is f, so we need to solve for that. Okay, how are we going to do that? Well, 1.5 times 4,000 is equal to 6,000. Since we have f times 4,000, I'm going to write that as 4,000f, so that's just like instead of x times 2, we would write 2x. I think it's a little bit easier to think about this way. All right, and then of course we didn't do anything to the left-hand side. That's still 4,000. All right, now in this equation we have a 6,000 here and a 5,000 here. Adding those together, we get 6,500 minus 4,000f, and that's still equal to 4,000 on the left-hand side. We then subtract 6,500 from each side. Those, of course, cancel out. And then we have negative 4,000 f on the left. Sorry, that's the right. We have negative 2,500 on the other side. And now we divide each side by 4,000. Sorry, negative 4,000 to get f by itself. Those cancel. And then negative 2,500 divided by 4,000 is 0.625. All right. So this is our fishing level. We usually think about that as a percentage, which of course we've practiced this already in this class. We move the decimal place 2 to the right, so we get 62.5% of the population should be fished. All right, so then the final thing that we want to do is to kind of, up here it asked us to write a new difference equation. So all we're going to do for that is take this difference equation that we wrote right here and simply replace our f with the decimal version. All right, so I'm going to kind of scroll this down here. So our new, why isn't that working? There we go. New difference equation is x sub n plus 1 equals 1.5xn minus 0.625 x sub n plus 500. All right, and again, what does that mean? This means that it's 1.5 times the fish population, which accounts for the growth rate of 50%. And then the minus 0.625 x sub n means we are taking away through fishing 62.5% of the population. This is fine. It's not the best way to write the difference equation. We should take these two terms that both have x sub n in them and combine them. So that gives us x sub n plus 1. If we do 1.5 minus 0.625, that gives us 0.875 x sub n. And then we have plus 500. And then I'll just rewrite that our x sub 0 is 1,000. This is our new difference equation.